Chapter 5, Aldehyde and Ketone. Introduction. Aldehyde and ketone constitute two isomeric series of compounds, both of which contain the carbonyl group in their molecule and are therefore collectively known as carbonyl compound. Aldehyde have one hydrogen atom and one alkyl or aryl group linked to the carbonyl group, while ketone have two alkyl or aryl group attached to the carbonyl group, as shown below. The aldehyde are said to contain the functional group CHO, or commonly referred to as aldehyde group, while ketone contain the functional group C double bond O, generally termed as ketonic group where when present in ketone. Ketone in which the group R and R dash attached to the ketonic group are the same are termed as simple ketone, and those in which R and R dash represent different group are known as mixed ketone. The presence of carbonyl group in both aldehyde and ketone is responsible for the close similarity in their method of preparation and property. However, due to presence of free hydrogen atom in their molecule, aldehyde are more reactive than ketone and also differ from them in certain aspect. Structure of carbonyl group. The carbon-oxygen double bond of carbonyl group is composed of alpha bond and an pi bond. Moreover, in the molecule of aldehyde and ketone, the carbon atom of the carbonyl group is also joined to two other atoms by sigma bond. Thus, the carbonyl carbon is involved in the formation of three sigma bond and one pi bond. According to molecular orbital theory, the carbonyl carbon of aldehyde and ketone make use of three sp2 hybrid orbital in forming the three sigma bond. As such, these bonds lie in the same plane with angle of approximately 120 between them. The pi bond between the carbon and oxygen is formed by one sideway overlap of remaining half-filled p orbital of carbon with a similar orbital of oxygen. The above discussion make it clear that the carbonyl carbon, oxygen and the two atoms directly attached to the carbonyl carbon lie in the same plane, one plane. The planar nature of part of molecule which immediately surround the carbonyl carbon is supported by electron diffraction and spectroscopy study of aldehyde and ketone. Another important aspect of the structure of carbonyl group arises from the different electronegativities of carbon and oxygen atom. Due to its greater electronegativity, the oxygen atom attracts the electron of the double bond, particularly the pi electron cloud, strongly toward itself. As a result, the electrons are not equally shared, and there is great electron density around the oxygen atom than around the carbon atom. In other words, carbonyl group is a polar group, oxygen having a small negative charge and carbon having a small positive charge. The polar nature of carbonyl group is probably best indicated by representing it as a resonance hybrid of the following two structures. The larger dipole moment of aldehyde and ketone support the polar character of the carbonyl group. Nomenclature. Aldehyde, they are named either according to the common or IUPAC system as explained below. Common system. In this system, aldehyde are named after the acid which they give rise to on oxidation. The suffix ic acid of the name of the acid is replaced by the word aldehyde. The CH3CHO give acetic acid on oxidation and is therefore named as acetaldehyde. Similarly, form benzoic acid on oxidation and is therefore named as benzaldehyde. This system is mainly used for aromatic and simple aliphatic aldehyde. IUPAC name. These names are given in accordance with the general IUPAC rule. The longest chain carrying the CHO group is selected. The corresponding word root and the primary suffix are written. This is followed by attaching the suffix al in place of final e. The position of substituent, if any, are indicated by suitable number. The aldehyde carbon always getting the number 1 because it is a chain terminating group. For this reason, the number of aldehyde carbon is not usually mentioned. It is taken for granted that it must be a number Ketone. The two system of naming ketone are as follow. Common name. Common name of ketone are obtained by adding the word ketone to the name of the alkyl or aryl group present in the molecule. These names are mainly used for aromatic and simple aliphatic ketone. For example, CH3CO CH2CH3 is named as methyl ethyl ketone. IUPAC name. IUPAC name of ketone carry the suffix on and are given according to the usual rule. The longest chain containing the carbonyl group is selected. From the name of the corresponding hydrocarbon, the suffix is replaced by on. The carbon of the ketonic group is assigned the minimum possible number along the straight chain of carbon atom, and the substituent group carries other suitable number. For example, is named as 4-methyl pentatone. Certain ketone, particularly aromatic ketone, are allowed to retain their common name. For example, acetophenone, benzophenone. Formation of aldehyde and ketone. Formation of aldehyde. Aldehyde are formed during many chemical reactions. Of these, we would describe only those important reactions which are actually used for a preparative purpose. Oxidation of primary alcohol. Aldehyde can be obtained by the oxidation of primary alcohol. However, this method suffers from a serious limitation because the aldehyde formed are further oxidized to carboxylic acid. This is primary alcohol oxidized to aldehyde, which is oxidized to carboxylic acid. The oxidation of aldehyde to carboxylic acid generally take place even with milder oxidizing agent than those required for the oxidation of primary alcohol to aldehyde. Therefore, it is difficult to stop the oxidation up to aldehyde stage. This problem can be overcome if the aldehyde form is removed from the reaction mixture by its distillation as soon as it is formed. It is often possible to do so because the aldehyde has lower boiling point than corresponding alcohol and they can be distilled away from reaction mixture. As shown above, the oxidizing agent usually employed in the above reaction in a solution of potassium dichromate in dilute sulfuric acid. However, if the alcohol has poor solubility in water, a solution of chromic anhydride in water, acetone and sulfuric acid is commonly used. This is known as Jones reagent. Special oxidizing agent. The above method of preparing aldehyde involves the distillation of aldehyde from the reaction mixture as soon as it is formed cannot be used in case of higher aldehyde having high boiling point. Therefore, some special oxidizing agents have been developed for preparing aldehyde from alcohol. For example, Syrets reagent or Collins reagent. It consists of a complex formed by careful addition of CrO3 to excess of pyridine. A solution of above complex in methylene dichloride oxidizes the primary alcohol to the aldehyde stage. Corey's reagent. It consists of pyridinium chlorochromate formed by mixing chromium trioxide, pyridine and HCl. It is also used in methylene dichloride solvent to convert primary alcohol into aldehyde. Pyridinium dichromate. It is obtained by mixing pyridine, potassium dichromate and HCl in CH2Cl2. Advantage of oxidation of alcohol with above reagent. As is obvious, advantage of using any of the above three reagents is that they restrict the oxidation of primary alcohol to aldehyde stage. This is because these reagents are used in non-aqueous medium and therefore do not allow the formation of aldehyde hydrate to take place during oxidation. Since aldehydes themselves are not as easily oxidized further as aldehyde hydrate, the reaction stop at the aldehyde stage. In case of oxidation by usual oxidizing agent such as acidic potassium dichromate and Jones reagent, the reaction are carried out in aqueous medium, whereas aldehyde formed are converted into aldehyde hydrate which are readily oxidized to carboxylic acid. Another advantage of using this reagent is that carbon-carbon double bond if present in the starting alcohol are not oxidized. Disadvantage of using above reagent. The use of special reagent discussed above for the oxidation of alcohol lead to the formation of chromium containing waste product which are environmentally very hazardous. At the same time, these reagents are quite expensive and are therefore not frequently used during laboratory oxidation reaction of alcohol. Catalytic dehydrogenation of primary alcohol. The oxidation of primary alcohol to yield aldehyde can also be brought about by passing the alcohol vapor over copper heated. The process is generally referred to as dehydrogenation as it involves the direct elimination of hydrogen. The dehydrogenation process does not involve the risk of further oxidation of aldehyde formed. Reduction of acid chloride Rosenman reaction. The partial reduction of acid chloride for another method for the formation of aldehyde. The reaction is usually brought about by passing hydrogen through a hot solution of acid chloride in xylene. The presence of a suitable catalyst. The catalyst employed is palladium deposited on barium sulfate, and the reaction is stopped as soon as the evolution of HCl gas ceases. This helps to prevent further reduction of aldehyde formed into alcohol. Nowadays, lithium tertiary butoxyaluminium hydride (Li) is being used to reduce acid chloride into acetaldehyde. An advantage of using this reagent is that it does not affect any other easily reducible group present in the molecule. Acid chloride used in this reaction are themselves usually obtained by the action of thionyl chloride or phosphorus halide on carboxylic acid. Thus, aldehyde can be obtained from carboxylic acid through the formation of acid chloride from 1,3-dithiones. The most recent method for the synthesis of aldehyde is by use of 1,3-dithiones. 1,3-dithiones is a non-aromatic heterocyclic compound containing two sulfur atoms. It can easily converted into its anion by treatment with alkyl lithium. The anion act as a strong nucleophile and react with alkyl halide to form alkyl derivative of 1,3-dithione. This derivative is hydrolyzed in presence of Hg2 positive ion to form the aldehyde. Catalytic decomposition of carboxylic acid. Aldehyde can also be obtained from carboxylic acid by passing the vapors of a mixture of methanoic acid and another carboxylic acid over manganese oxide at 573 K. Carboxylic acid other than methanoic acid plus methanoic acid give rise to aldehyde. Some other method which can also be used for the preparation of aldehyde are given below. Ozonolysis of alkene. In this method, the ozonide formed by reaction between an alkene and ozone is decomposed with a reducing agent to yield aldehyde and ketone. Stephan reaction. Alkyl cyanide on reduction with stannous chloride and hydrochloric acid give rise to aldimine. The aldimine get hydrolyzed on warming with water to yield an aldehyde. Oxidation of methyl benzene. Aromatic aldehyde can be prepared by oxidation of methyl benzene by different method as given below. Oxidation of methyl benzene to aldehyde is usually carried out with chromium trioxide in acetic anhydride. The gem diacetate initially formed is isolated and hydrolyzed to get the aldehyde. Since the intermediate gem diacetate cannot be oxidized further, there is no chance of the formation of carboxylic acid. Controlled oxidation of methyl benzene to aldehyde can also be carried out with chromyl chloride or manganese dioxide. The reaction involving chromyl chloride as oxidizing agent is known as Itard reaction. For example, toluene in presence of CrO2Cl2 give rise to addition complex, which in presence of H2O give rise to benzaldehyde. It is also possible to convert methyl benzene into aldehyde by free radical halogenation of methyl benzene followed by hydrolysis of gem dihalide formed. For example, toluene plus Cl2 give rise to benzyl chloride plus HCl. Gutterman-Koch reaction. This reaction constitutes a convenient method for preparing aromatic aldehyde by treating benzene or other aromatic compound with a mixture of CO and HCl in the presence of a lavish acid and copper chloride. In a similar reaction as Gutterman reaction, HCl is used in place of CO. The aldehyde initially formed is hydrolyzed to get the corresponding aromatic aldehyde. Riemann-Tiemann reaction. This is a convenient method for the preparation of phenolic aldehyde, particularly those in which the aldehyde group is prepared in orthoposition to the phenolic group. The reaction is carried out by treating a phenol with chloroform and aqueous sodium hydroxide solution. Formation of ketone. The important method of preparing ketone are described below. Oxidation of secondary alcohol. Ketone can be easily prepared by the oxidation of secondary alcohol. The oxidation is usually affected by acidified sodium or potassium dichromate, potassium permanganate, or chromium dioxide in a variety of solvent. There is no risk of further oxidation of ketone taking place as ketones are not easily oxidized. Open your alcohol oxidation. Secondary alcohol can be oxidized by refluxing with acetone in the presence of aluminium isopropoxide or aluminium tertiary butoxide. The alcohol taken is oxidized to the corresponding ketone while acetone is reduced to isopropyl alcohol. This process is particularly suitable for oxidation of unsaturated alcohol and is known as open-air alcohol oxidation. Catalytic dehydrogenation of secondary alcohol. Ketone can also be obtained by the dehydrogenation of secondary alcohol by passing their vapor over copper heated to 475 to 575 K. Reaction of nitrile with Grignard reagent or organolithium compound. Reaction of nitrile with either a Grignard reagent or an alkyl lithium followed by hydrolysis yield a ketone. Reaction of acid chloride with organocadmium compound. Acid chloride react with suitable organocadmium compound to yield ketone. R may be any alkyl or aryl group, but R dash must be an aryl or primary alkyl group. This is because organocadmium compound containing only aryl or primary alkyl group are sufficiently stable for use. These days, another type of organometallic compound known as lithium organocuprates RuCuLi, where R may be any alkyl or aryl group, are being increasingly used for preparing ketone from acid chloride because the reaction involved does not suffer from any drawbacks. Lithium organocuprate are themselves obtained by reaction because cuprous halide and organolithium compound. Since acid chloride can themselves be obtained from carboxylic acid, the above reaction enables us to prepare ketone from carboxylic acid. Reaction of carboxylic acid with alkyl or aryl lithium. When a carboxylic acid is treated with 2 molar equivalent of alkyl or aryl lithium followed by reaction with water, it leads to the formation of a ketone. Ketone can also be obtained by the distillation of calcium salt of carboxylic acid other than formic acid from 1,3-dithionase. This reaction involves the conversion of 1,3-dithione into dialkyl derivative and the subsequent hydrolysis of the dialkyl derivative to form ketone. Friedel-Crafts acylation. This method is specifically used for the preparation of ketone in which the ketonic group is attached to at least one aromatic ring. It consists in treating an aromatic compound with an acid halide In the presence of a lavish acid such as anhydrous aluminum chloride, it is also possible to use an acid anhydride in place of acid chloride. Some other method which can also be used for the preparation of ketone are given below. Hydration of alkyne, hydration of homologous of acetylene lead to the formation of methyl ketone. For example, 2-butene presence of HgSO4 H2SO4 give rise to methyl ethyl ketone. Ozonolysis of alkene. Ozonolysis of alkene, in which the double bond is next to a position of branching of the carbon chain, also lead to the formation of ketone. Acetoacetic ester synthesis. Methyl ketone can be conveniently obtained from alkyl derivative of ethyl acetoacetate, popularly known as acetoacetic ester. This method involves the conversion of acetoacetic ester into sodioacetoacetic ester by treatment with sodium ethoxide. Subsequently, acid thus obtained is heated to get methyl ketone. Physical properties of aldehyde and ketone. Physical state. With the exception of formal aldehyde, which is a gas at a room temperature, most of the common aldehyde and ketone are liquid at ordinary temperature. The lower molecular weight aldehyde have sharp and rather unpleasant smell, but high molecular weight aldehyde and ketone are pleasant smelling. In fact, some ketone are used in perfumes. Boiling point. The boiling point of aldehyde and ketone are lower than those of alcohol and carboxylic acid of approximately equal molecular weight. This is due to the fact that unlike alcohol and acid, there are no effective hydrogen bond between aldehyde or ketone molecule. However, due to their highly polar nature, there is appreciably intermolecular attraction in aldehyde or ketone. As such, their boiling point are higher than those of hydrocarbon and ether of comparable molecular weight. Melting point. Melting point of aldehyde and ketone do not show any regular trend with increase in molecular weight. Solubility. Aldehyde and ketone containing up to 5 carbon atoms are more or less soluble in water, but the solubility fall rapidly with increasing molecular weight. Higher member as well as aromatic aldehyde and ketone are practically insoluble. However, all aldehyde and ketone are readily soluble in organic solvent. The solubility of lower aldehyde and ketone in water is due to the formation of intermolecular hydrogen bond involving the carbonyl group as shown ahead. But the increase in the size of non-polar group attached to carbonyl carbon does not allow hydrogen bonding to take place, so the solubility decreases sharply with the increase in molecular weight. Chemical properties of aldehyde and ketone. Aldehyde and ketone are a highly reactive compound which exhibit a marked similarity in their chemical behavior. That is, of course, due to the presence of carbonyl group in both the type of compound. But an important question which arises is as to what makes the carbonyl group so reactive and what type of reaction does it bring about in aldehyde and ketone. It would be quite appropriate to deal with this question before discussing the actual chemical reaction. Reactivity of carbonyl group toward nucleophilic attack. The carbonyl group contains a double bond between two heteroatoms, carbon and oxygen. Since oxygen is more electronegative than carbon, the bonded electron, particularly the pi electron, are pulled strongly toward oxygen. As a result, the carbonyl group is very polar group. The carbonyl carbon being electron deficient and the carbonyl oxygen being electron rich. Moreover, the carbonyl group is flat and can therefore be readily attacked from above or below in direction perpendicular to the plane of the group. Consequently, the carbonyl group is highly reactive group. It is quite obvious that the reaction of the polarized carbonyl group could be initiated either by the attack of a nucleophile reagent on electron deficient carbon or the attack of an electrophilic reagent on the electron rich oxygen. However, out of electron deficient carbon and electron rich oxygen, the former is relatively less stable. Therefore, most of the reaction of aldehyde and ketone involve the initial attack of nucleophilic reagent on the relatively less stable electron deficient carbonyl carbon and the ultimate lead to the formation of addition product. As these reactions are described as nucleophilic addition reaction. Mechanism of nucleophilic addition reaction. The nucleophilic addition to a carbonyl compound is initiated by the attack of nucleophile on the carbonyl carbon. This leads to the formation of transition state in which the hybridization of carbon change from sp2 to sp3 at the same time Oxygen begin to acquire pi electron of carbon double bond oxygen as shown below. As the pi electron of the carbon double bond oxygen bond has completely transferred to oxygen, a tetrahedral intermediate is formed in which the carries negative charge. This intermediate pick up a proton to form the addition product. The attacking nucleophile reagent can be either a negatively charged ion or a neutral molecule. Role of acid catalyzed in nucleophilic reaction. The nucleophilic attack on the carbonyl group can be catalyzed by presence of acid. The hydrogen ion generated by the acid rapidly combined with the electron-rich oxygen of the carbonyl group. This leads to a decrease in the activation energy for nucleophilic attack as it enables oxygen to acquire the pi electron without having to accommodate a negative charge as shown ahead. It should be noted, however, that if the reaction solution is made too acidic, the H positive ion would combine with the attacking nucleophilic reagent as well. This would suppress the concentration of attacking nucleophilic species and thus adversely affect the nucleophilic attack. Therefore, it is important to control the pH of the reaction mixture in such reaction. It should be noted that addition of powerful nucleophile does not require any acid catalysis at all. It is only the weak nucleophiles such as alcohol and ammonia derivative which need the assistance of a little acid catalysis. Relative reactivities of aldehyde and ketone in nucleophilic reaction. It has been observed that in nucleophilic addition reaction, aldehyde are more reactive than ketone, and aliphatic aldehyde or ketone are more reactive than aromatic one. This can be easily explained in terms of steric and electronic factor as discussed below. Steric factor. In the transition state of nucleophilic attack on carbonyl carbon, the carbons start forming a bond with the attacking species and tend to change from trigonal to tetrahedral stage. Now, the larger the size of alkyl or aryl group attached to the carbonyl group, the more crowded will be the transition state. Thus, the formation of transition state would be more difficult in case of ketone and in case of aldehyde, since ketone contain two alkyl or aryl group attached to the carbonyl group, while aldehyde have one hydrogen and only one alkyl or aryl group. As such, ketone would be less reactive than aldehyde. Similarly, among as the ketone themselves, those containing bigger group would be less reactive than the ones containing smaller group. Electronic factor. In addition to steric factor, electronic factor are also responsible for the great reactivity of aldehyde as explained below. Aldehyde, aliphatic aldehyde and ketone. Alkyl group have electro-releasing inductive effect and their presence tend to destabilize the transition state by enhancing the negative charge developing on the oxygen. Since aldehyde contain only one alkyl group while ketone have two such groups, the transition state resulting from a ketone is destabilized to greater extent than that resulting from an aldehyde. As such, the transition state is more difficult to form in case of ketone and consequently ketone are less reactive. It can be easily understood that presence of electron attacking substitute on alkyl group would enhance the reactivity of aldehyde and ketone in nucleophilic reaction. Aromatic aldehyde and ketone. An aromatic nucleus directly attached to a carbonyl group may be expected to increase the reactivity of aldehyde or ketone as it tends to stabilize the transition state due to its electron withdrawing inductive effect. However, the aromatic nucleus stabilizes the reacting aldehyde or ketone even more due to resonance interaction with the pi electron as shown below. The result is that the aryl group causes a net decrease in the reactivity of carbonyl group. As such, aldehyde or ketone having aryl group directly attached to the carbonyl group are less reactive than the aliphatic counterpart. It may be noted that presence of electron withdrawing substituent at ortho and para position on the benzene ring increase the reactivity of aromatic aldehyde and ketone. Electron donating group have the opposite effect. Acidity of alpha hydrogen. Besides providing a site for nucleophilic addition to aldehyde and ketone, the carbonyl group is also responsible for the acidity of alpha carbon atom. In the presence of a base, a hydrogen attached to alpha carbon atom can split off in the form of H positive ion to form a carbon ion. The carbon ion thus formed account for many reactions of aldehyde and ketone. The acidic nature of alpha hydrogen and its removal in the presence of a base can be attributed to the fact that the resulting carbon ion is a resonance stabilized by interaction with the carbonyl group as shown below. It is interesting to note that participation of carbonyl group in the resonance stabilization of the carbon ion is also due to the ability of oxygen to accommodate the negative charge. Having discussed the fundamental aspect of reactivity of aldehyde and ketone, let us now deal with the various chemical reactions actually undergone by these compounds. Nucleophilic addition reaction. A large variety of nucleophilic reagent can attack the carbonyl group to yield addition compound in which the carbonyl carbon is bonded to some atom of the attacking reagent. In addition, the addition compound thus found may itself represent the final product, or it may be undergone a subsequent elimination or substitution reaction to furnish a more stable product. Nucleophilic addition reaction leading to the formation of new bond between carbonyl carbon and the atom of some other element such as oxygen, nitrogen or sulfur. Addition of sodium bisulfite. Nearly all aldehyde and many ketone react with a saturated sodium bisulfite solution to form crystalline solid referred to as bisulfite addition compound. In these compound, carbonyl carbon get bonded to sulfur of the attacking reagent. It is a reversible reaction, but on using saturated solution of sodium bisulfite, the equilibrium is shifted to the right and the addition product get precipitated. Ketone containing bulky group do not react with NaHSO3 due to steric hindrance. Mechanism. The reaction involves nucleophilic attack of carbonyl carbon by bisulfate ion, and the complete process may depicted as shown below. Reaction with ammonia derivative. Aldehyde and ketone undergo nucleophilic addition with certain compound related to ammonia, such as addition compound initially formed eliminate a molecule of water to yield compound containing double bond between carbon and nitrogen. As such, these reactions are also termed as addition elimination or condensation reaction. If we represent the ammonia derivative by general formula NH2G, the formation of final product may be depicted as the product formed are usually crystalline solid having sharp melting point and are used for the identification of aldehyde and ketone. Moreover, at these products can be decomposed by boiling with dilute mineral acid to regenerate the parent carbonyl compound. They can be used for purification of aldehyde and ketone. Mechanism. All the ammonia derivative represented by the formula H2 and G are basic compound having a lone pair of electron on nitrogen. They act as weak nucleophile reagent and their reaction with carbonyl compound is catalyzed in the presence of acid. The hydrogen ion protonate the carbonyl oxygen, and as a result the carbonyl carbon is very readily attacked by the basic nitrogen compound. Reaction and condition of control of pH. It must be pointed out that while using acid as a catalyst in this reaction, it is very important to have proper acidity in this reaction mixture. If the reaction mixture is made highly acidic, the hydrogen ion begin to protonate the attacking ammonia derivative too. The protonated derivative does not have any unshared electron on nitrogen and is no longer nucleophilic. This naturally means that too much acidity would decrease the rate of reaction rather than catalyze it. In other words, the reaction medium should have just right acidity or pH to ensure maximum rate of reaction. The important reaction of ammonia derivative are discussed below. Reaction with hydroxylamine. Aldehyde and ketone react with hydroxylamine to form oximes. Reaction with hydrazine. Aldehyde and ketone react with hydrazine to form hydrazone. Reaction with phenylhydrazine. Reaction of aldehyde and ketone with phenylhydrazine result in the formation of phenylhydrazone. Reaction with semicarbazide. Both aldehyde and ketone react with semicarbazide forming semicarbazones. Reaction with ammonia. The reaction of aldehyde and ketone with ammonia are of no importance. Most of the aldehyde initially formed addition product with ammonia known as aldehyde ammonious. These compounds are unstable and lose water to form aldehydes, which in turn get polymerized. Formal aldehyde react differently to form hexamethylene tetramine, which is used as urinary antiseptic under the name urotropine. Ketone generally give complex polymeric product with ammonia. Reaction of aldehyde and ketone with the primary and secondary amine to form amine and enamines is discussed later. Addition of alcohol. Aldehyde and ketone react with alcohol in presence of anhydrous acid catalyst to form ethereal compound called acetals. Acetal contain new bond between carbonyl carbon and oxygen atom of alcohol. The product formed by reaction between ketone and alcohol were earlier called ketone, but now the term acetal is used for the product formed from aldehyde as well as ketone. Mechanism. To start with, a molecule of alcohol add to the carbonyl group of the aldehyde to form a hemiacetal. With a few exceptions, the intermediate hemiacetal is not stable enough to be isolated. On the other hand, under the catalytic influence of the acid, the hemiacetal is readily converted into the stable acetal. It may be noted that the conversion of hemiacetal into acetal involves the replacement of OH by an alkoxy group, and its mechanism is similar to SN1 mechanism for the formation of an ether from an alcohol. Formation of cyclic acetal. Both aldehyde and ketone react with ethylene glycol in presence of paratoluene sulfonic acid to yield respective cyclic acetal. Use of acetal as protecting group. Unlike aldehyde and ketone, acetal are very stable two bases but are hydrolyzed back to aldehyde and ketone upon treatment with acid. Therefore, their formation is used as a mean of protecting a carbonyl group in certain reaction where in otherwise interfere with the desired reaction. Protection is the process of preventing a group from taking part in an undesired reaction by converting it into a new, less reactive group from which it can be regenerated as a later stage. For instance, let us imagine that we want to carry out the reduction of ester group of a ketoester into an alcoholic group. A reducing agent which bring about the reduction of ester group would normally reduce the keto group as well. Therefore, selective reduction of ester group is not possible. The problem can be solved by first converting the keto group in an acetal. The resulting acetal is then subjected to reduction with LiAlH4. An ester group would be reduced to alcohol, but acetal would remain unaffected. The acetal group is then hydrolyzed back to keto group with aqueous acid. This is illustrated below by considering the formation of 4-hydroxy pentatone from ethyl 4-oxopentanone. Nucleophilic addition reaction leading to the formation of carbon-carbon bond carbanion as nucleophilic reagent. We would now take up reaction in which carbanion constitute the attacking nucleophilic reagent. Most of these reactions are of great synthetic importance since they lead to the formation of carbon-carbon bond, addition of hydrogen cyanide. Hydrogen cyanide add to almost all aldehyde and ketone to form alpha hydroxy nitrile, usually known as cyanohydrine. Mechanism. The reaction involved the initial nucleophilic attack on carbonyl carbon by a strongly basic carbanion, cyanide ion. The process is completed by the attachment of a hydrogen ion to oxygen. Addition of Grignard reagent. Grignard reagent react with aldehyde and ketone to form addition product which are readily decomposed by water, preferably in the presence of an acid such as HCl or H2SO4 to yield alcohol. Mechanism. In the formation of addition product, the nucleophilic carbanion portion of Grignard reagent add to the carbonyl carbon while the remaining portion get attached to oxygen as depicted below. It may be pointed out depending upon the starting aldehyde or ketone, the alcohol obtained as the final product may be primary, secondary, or tertiary alcohol. Formal aldehyde yield a primary alcohol, other aldehyde give secondary alcohol, while ketone furnish tertiary alcohol. Aldol condensation. In the presence of a dilute base, two molecules of an aldehyde or a ketone having alpha hydrogen atom combine to form beta hydroxyl aldehyde or beta hydroxy ketone. The hydroxyl aldehyde obtained from acetaldehyde was originally named aldol, and consequently the reaction came to be known as aldol condensation. It may be noted that in every case the product contains a carbon-carbon bond between the carbonyl carbon of one molecule and the alpha carbon of the second. Mechanism. The base remove an alpha hydrogen from aldehyde or ketone molecule to form a resonance stabilized carbanion or enolate ion. This ion, being strongly nucleophilic, attack the carbonyl carbon of a second molecule of aldehyde or ketone to yield an anionic intermediate. The intermediate then abstract a proton from water to form the aldol. Synthetic importance. The beta hydroxylaldehyde or beta hydroxy ketone obtained from the base catalyze aldol condensation are easily dehydrated on warming with acid to form alpha beta unsaturated carbonyl compound. For example, alpha beta unsaturated carbonyl compound in turn can be oxidized to alpha beta unsaturated acid or reduced selectively to alpha beta unsaturated alcohol. Therefore, aldol condensation commands considerable synthetic importance. It can be employed for the preparation of beta hydroxycarbonyl compound, alpha beta unsaturated carbonyl compound, alpha beta unsaturated carboxylic acid, alpha beta unsaturated alcohol, etc. Aldol condensation, crossed aldol condensation. Aldol condensation can also take place between two different aldehyde and ketone, or aldehyde and a ketone. Such an aldol condensation is referred to as crossed aldol condensation. If both the reacting carbonyl compound contain alpha hydrogen atom, cross aldol condensation can yield a product of four different products, which are usually quite difficult to separate. Therefore, such a reaction is seldom carried out. Moreover, by a suitable choice of experimental condition, it is possible to suppress the formation of one of the product so as to get only one compound as the main product. For example, if acetaldehyde is slowly added to a mixture of benzaldehyde and aqueous alkali, the final product is mainly cinnamaldehyde. Similarly, reaction between acetone and formaldehyde yield mainly 4-hydroxy-2-butanone. It may be pointed out in crossed aldol condensation, the aldehyde or ketone lacking in alpha hydrogen cannot form the attacking carbon ion. It merely serves as a site for the nucleophilic attack by the carbon anion formed by the other reactant. Claisen reaction. This reaction is special case of crossed aldol condensation and may be defined as base catalyzed condensation of an aromatic aldehyde and an aliphatic aldehyde or ketone to form alpha beta unsaturated aldehyde or ketone. For example, reaction between acetaldehyde and benzaldehyde in presence of aqueous alkali yield mainly cinnamaldehyde. In the above reaction, initially two products are obtained. One is the self condensation product of acetaldehyde, while the other is a cross condensation product, which is the main product. This product is mainly beta OH group is activated by phenyl group loses water immediately to form alpha beta unsaturated aldehyde. Benzoin condensation. Aromatic aldehyde which do not contain alpha hydrogen atom cannot undergo simple aldol condensation. However, in the presence of potassium cyanide, they undergo self condensation in a different manner to form product known as benzone. Perkin reaction. Closely related to aldol condensation is the Perkin reaction, which involves the addition of acid anhydride to aromatic aldehyde in the presence of base. The base commonly employed is the sodium salt of carboxylic acid, from which the anhydride is derived, and the addition compound initially formed ultimately yield an alpha beta unsaturated acid. Mechanism. In the presence of base, the acid anhydride loses a hydrogen ion from alpha carbon to form a carbon anion which add to the carbonyl group of the aldehyde. The resulting ion after protonation form an aldol-like product. This product undergo dehydration in the presence of acid anhydride to form a mixed anhydride which get hydrolyzed to form the alpha beta unsaturated acid. The complete mechanism is shown below by considering the reaction between benzaldehyde and acetic anhydride in the presence of sodium acetate. Noy-Weinagel reaction. This is another reaction related to aldol condensation. It involves the condensation between an aldehyde or ketone and a compound having an active methylene group in the presence of a base which is usually an amine. In general, the reaction may be represented as the condensation product formed above can be decarboxylated to get an alpha beta unsaturated acid. Mechanism. The base remove a proton from the active methylene compound to form a resonance stabilized carbon ion. This attack the carbonyl carbon. The ion thus formed undergo protonation followed by dehydration. Mannich reaction. This is a reaction between an aldehyde and amine and an active methylene compound. The aldehyde usually taken is formal aldehyde and the amine compound employed is dimethylamine. The reaction can take place in neutral acidic or alkaline media. In the product formed is popularly known as managed base. Mechanism. To start with, formal aldehyde react with amine to form an iminium salt. The iminium ion get attacked by enolate ion of the active methylene compound to form the final product. The Witting reaction. This is the reaction between aldehyde or ketone and a type of compound known as phosphorus yields to form substituted alkene. The phosphorus yield generally used an alkyl dye in triphenyl phosphorins or an Ardeshmi equivalent is hydrogen or alkyl or aryl group. The overall reaction may be represented as it is clear that the reaction result in the replacement of carboxylic oxygen, formation of phosphorus yield or Witting reagent. The phosphorus yield required in the reaction and themselves obtained by the action of a base on suitable alkyl triphenyl phosphoronium halide. The base remove a proton from the alpha carbon atom of alkyl group of the phosphoronium salt to generate the yield as shown below. The base generally employed in the above process is methyl sulfine carbanion. Some organolithium compounds such as N-butyl lithium or phenyl lithium, the solvent commonly used in dimethyl formol or tetrahydrofuran. The yield obtained as shown above are not isolated but are directly made to react with the aldehyde or ketone in the solution form. Reduction. Aldehyde and ketone can be easily reduced to form various products depending upon the structure of reducing agent employed. Reduction to alcohol. Aldehyde can be reduced to primary alcohol and ketone to secondary alcohol either by hydrogenation in the presence of catalysts such as nickel, palladium or platinum or by reducing agent like lithium, aluminum hydride and sodium borohydride. Reduction to methylene group. The carbonyl group in aldehyde and ketone can also be reduced to methylene group to form hydrocarbon. This is generally achieved by following two methods. Clemmensen reduction. This involves the reaction of aldehyde or ketone with zinc amalgam and concentrated hydrochloric acid. The reaction worked well for ketone and not for aldehyde. Mechanism. Several mechanisms have been proposed for this reaction. One of the proposed mechanism is as followed. Wolff-Kishner reduction. In this method, the aldehyde or ketone is heated with hydrazine and a strong base like potassium hydroxide or potassium tertiary butoxide. The reaction is initiated by formation of hydrazone of aldehyde or ketone with undergo subsequent changes as shown below. Reduction with HI. Aldehyde and ketone can also be reduced to correspond hydrocarbon by heating with HI in presence of red phosphorus. Bimolecular reduction. In the presence of magnesium, usually employed in the form of amalgam, aldehyde and ketone undergo bimolecular reduction to form symmetrical glycol, generally known as pinacol. The name pinacol was initially employed for the glycol obtained from acetone, but it has come to be used for all symmetrical glycol. Mechanism. Pinacol reduction involves the formation of a bond between two carbonyl carbon and proceed through the following mechanism. Magnesium donate one electron each of two molecules of carbonyl compound to form an adduct. These contain two unpaired electrons, one on each carbonyl carbon, which unite to form a carbon-carbon bond to furnish the magnesium salt of pinacol. The result is ultimately hydrolyzed to form pinacol. The mechanism is unusual in the sense that it involves initial attack on oxygen rather than carbon. Reductive amination. Many aldehyde and ketone change into amine on treatment with hydrogen and ammonia in presence of a catalyst such as nickel. The process is known as reductive amination and probably proceed through the intermediate formation. The possibility of further reaction between aldehyde or ketone and the amine formed can be restricted by employing suitable proportion of the reactant. Oxidation. The behavior of aldehyde and ketone toward oxidizing agent constitute the main difference in the chemical properties of these two classes of carbonyl compound. Due to the free hydrogen atom attached to the carbonyl carbon, aldehyde are easily very readily oxidized even by mild oxidizing agent to form carboxylic acid having the same number of carbon atom as the original aldehyde. Ketone on the other hand resist oxidation and get oxidized only by strong oxidizing agent. Oxidation of aldehyde. As stated above, aldehyde are readily oxidized by usual oxidizing agents such as KMnO4, K2Cr2O7, H2SO4, and dilute HNO3 to form corresponding acid. Mechanism of oxidation. Mechanism of aldehyde oxidation with a different oxidizing agent are not well established. In the chromium acid oxidation of aldehyde, it is believed that the aldehyde is first hydrated to a jam diol. The diol get oxidized via the formation of chromate ester as shown below. Reducing character. Since aldehyde are easily oxidized even by mild oxidizing agent, they act as a powerful reducing agent. Reduction of Tollens reagent. Tollens reagent is an ammoniacal solution of silver nitrate which contains silver in the form of silver ammonia complex ion. On adding an aldehyde to this reagent, the aldehyde is oxidized to carboxylate ion, which in ammoniacal solution form the ammonium salt of the acid. The silver ammonia complex is reduced to metallic silver, which get deposited as a silver mirror on the side of tube containing the solution. The reaction is therefore referred to as silver mirror test. Reduction of Fehling solution or Benedict solution. Fehling solution is obtained by mixing equivalent quantities of a solution of copper sulfate and a solution of sodium hydroxide and sodium potassium tartrate. The resulting solution contains a copper tartrate complex which furnish a small concentration of cupric ion. Benedict solution is comparable to Fehling solution and is obtained by mixing copper sulfate solution with a solution of sodium carbonate and sodium citrate. Thus it contains a copper citrate complex which furnish cupric ion. On reacting an aldehyde with Fehling or Benedict solution, the blue color of cupric ion is discharged from and a red precipitate of cuprous oxide is formed. Oxidation of ketone. It has already been stated that ketones are not easily oxidized. This is because the oxidation of ketone invariably involves cleavage of carbon-carbon bond and therefore it can be brought about only by strong oxidizing agent. The important oxidation of reaction of ketone are as follows. Oxidation to carboxylic acid. Strong oxidizing agents such as acidified potassium dichromate and concentrated nitric acid to yield a mixture of acid each containing lesser number of carbon atom than the original ketone. The reaction involves the attack only at the carbon atom adjacent to the carbonyl group. In case of unsymmetrical ketone, the attack takes place preferably at the adjacent carbon carrying lesser number of hydrogen atom. If both the adjacent carbon atom have same number of hydrogen atom, carbonyl group remain linked preferably to the smaller alkyl group. Haloform reaction. An important oxidation reaction of ketone is the haloform reaction of methyl ketone. It consists in reacting a methyl ketone with halogen in aqueous sodium hydroxide. As a result, the ketone is oxidized to form the sodium salt of an acid containing one carbon atom less than the ketone at the same time. Haloform is produced. The overall reaction may be represented as. The reaction is also used as a test for methyl ketone. When employed for this purpose, the hypohalite used is sodium hypoiodide because the iodoform formed separately out as a yellow PPT that can be easily identified. The reaction is termed as iodoform reaction and may be depicted as follows. Mechanism. When methyl ketone is treated with a halogen in aqueous sodium hydroxide, halogenation takes place at the carbon of the methyl group forming a trihaloketone. The carbonyl carbon of this trihaloketone is then attacked by hydroxide ion. As a result, cleavage of carbon-carbon bond between carbonyl carbon and the trihalomethyl group take place. This ultimately leads in the formation of a carboxylate ion and haloform as depicted ahead. Baeyer-Villiger oxidation. This reaction involves the conversion of ketone into ester by reaction with per acid. The formation of ester takes place due to introduction of an oxygen atom between carbonyl carbon and an alpha carbon. Mechanism. The reaction is catalyzed by acid and involves the addition of per acid to carbonyl carbon of ketone. The most important step in the reaction is the migration of group R- from carbon to electron deficient oxygen as shown below. In case of unsymmetrical ketone, the tendency of the group to migrate to electron deficient oxygen is in the order tertiary alkyl, secondary alkyl, phenyl, primary alkyl, methyl. In case of substituted aryl group, the order is para-methoxyphenyl, para-toluylphenyl, para-chlorophenyl. The migratory aptitude determines the final product formed in the reaction. For example, in the oxidation of acetophenone with perbenzoic acid, the final product is CH3COOC6H5 because phenyl group has a greater tendency to migrate to electron deficient oxygen than methyl group. It may be seen that net result of Baeyer-Villiger oxidation is that an oxygen is inserted in between carbon of carbonyl group and adjacent carbon of the group having migratory aptitude. Cannizzaro reaction. This is self-oxidation and reduction or disproportionation reaction, which is undergo by aldehyde having no alpha hydrogen. It consists in treating such as aldehyde with a concentrated aqueous or alcoholic solution of sodium or potassium hydroxide when an alcohol and a salt of carboxylic acid are produced. For example, formaldehyde plus concentrated solution of NaOH give rise to methyl alcohol plus sodium formate. Benzaldehyde plus concentrated solution of NaOH give rise to phenyl benzyl alcohol plus sodium benzoate. Mechanism. The reaction involves the addition of a hydroxide ion to an aldehyde molecule to form an anion. This anion transfers a hydride ion to a second aldehyde molecule as shown below. Cross Cannizzaro reaction. Cannizzaro reaction can also take place between two different aldehydes not having alpha hydrogen. It is known as crossed Cannizzaro reaction and lead to the formation of four different products. However, if one of the aldehyde is formaldehyde, the product consists of almost exclusive sodium formate and the alcohol derived from the other aldehyde. Thank you.